we have this space here, this Teichmüller space. We know parameterization of this space by length functions. I have some functions on this space. When I know the function, when I know all these functions at some point, then it determines completely the point. There's another parameterization. This is called Fenchel-Nielsen parameterization. And this now I'm answering a question which was asked by someone on the web. So what is this Fenchel-Nielsen parameterization? Again, I take some Pantz decomposition of the surface, decomposition into pairs of Pantz. So these are now geodesics. I take a geodesic pair of Pantz decomposition. Pantz decomposition, meaning that all these curves are, sorry, I forgot one, all these curves are closed geodesics. And since they are, you see, I start with a topological pair of Pantz decomposition that is just homotopy classes of disjoint curves, and then I make them all geodesic, and I explained to you that, did I say, or I say it now, that if, so on the surface, if I take this curve, and if they are represented by disjoint curves as topological curves, then the geodesics in their homotopy class are disjoint. I told you that in each homotopy class of curve, there is a geodesic. If the curves are disjoint, then the corresponding closed geodesics are disjoint also. This is some easy hyperbolic geometry, as I told you, in fact. Yeah, okay, so I take disjoint simple closed curves, maximal number. I take the corresponding geodesics, and I find this geodesic decomposition into pairs of Pantz. I have the length function, L1, L2, L3, L4. So we already discussed this problem. If I give you the values of L1, L2, L3, L4, L5, so all these functions, if I give you all the lengths, do I determine the surface? Is the surface completely determined? No, because instead of gluing like this, I could change the twist, right? I could change the twist. So there are associated to a geodesic pair of Pantz decomposition. So there's associated length parameters, and then twist parameters. Length parameters and twist parameters. The twist is some. It needs some convention, but you can imagine that I can. So here between these two surfaces, I just have I have a tube, a tube here and a tube here, and I want to, they have the same length, of course, they have the same length, and I can glue them, and I get a genuine hyperbolic structure. You see, around each point there's a disk which makes it, which makes this neighborhood of this point, neighborhood of a point in the hyperbolic plane. Okay. So everybody believes now that that there are length and twist parameters. Okay, and this is what makes the space, this space of dimension 6D minus 6, because if you make the count, then you find this number 6G minus 6. This is the Fenchel-Nielsen parametrization. You must, yeah. So I wanted to point out something. You see, if I do a full twist, what happens if I do the full twist? So no, not 180 degrees. I think I can count now better than you. It's 360 degrees. Okay. So if I cut the surface, then I turn by 360 degrees, and I glue again. Do I get the same surface or not? No. So our friend here knows that the answer is no. So for the others, you must remember that the surfaces are equipped with a marking, and when I say that the surfaces are the same, it means that the marking. You see, imagine a segment here. Let's say a geodesic segment. After the full twist, it will be something like that. Okay, so the homotopy class of this closed curve, the homotopy class of this initial closed curve, which where is my initially suppose I have a closed curve like this. After I do the full twist, the new homotopy class is this one in white. So the marking has changed. So these are different points in Teichmüller space. Okay, this is so this is one parametrization of Teichmüller space. There are other parameterizations. This is the most ancient one and the most, I mean, the one which is natural, which everybody can understand. Last time we talked about, I started talking about measured foliations. And then I told you that there's a space here, there's a boundary. There's a boundary to Teichmüller space, which is a space of measured foliations. And I want to explain this a little bit because I will have to use it later. So if you remember, we discussed foliations on surfaces, and we said that if the surface is not the torus, like here at surface of genus 2, that we must have necessarily singular points for a foliation. Okay, so one can imagine all kinds of singular points, but in this theory, there are only are allowed the following: allowed singular points. So either this one like this, or this one like this, or this one like this. So this is 3 prongs, or 3 separatrices, let's say 3 separatrices. 1, 2, 3, they separate into 3 portions of the plane. 3 locally, you have 3 separatrices, you have 4 separatrices, 5 separatrices, and so on. And this is one. Well, now I want to show you this. How do we do? We do this, and then we close the light. Where?
That's the remote.
Okay. It will come. Okay, so this is again, I like this picture. This is the first time Thurston talked about this. He distributed these notes. So this is interior singularities of measured foliations, p-pronged saddles. So this is p equals 3. This is p equals 4. And this is p equals 5, as I said. And then he has this picture. I mean, I have this picture, which is the last picture. Now, something important is when you have 2 measured foliations which are transverse to each other. So these foliations, and then you have one which is transverse to it, but here he is explaining what happens at the singular points. So they are transverse, and then at the singular points, the most natural thing happens. This is a 5-pronged singularity. No, sorry, it's a 3-pronged singularity for each of these measured foliations, and then they come. So the one is transverse to the other, means that at the singular point here, you have the 3 alternating prongs. And in the most natural way, this is 1, 2, 3, 4, and 4 is 8. And these are the only two singular points on this picture. And we talked about geographic maps. You know, geographic maps. You have also these perpendicular foliations by the parallels and the meridians and so on, and you are looking for best maps. And here also you will look for best maps between surfaces. All this is related, in fact. Okay, so I finished now with this picture. And I will tell you more about measured foliations now. Yes. Okay, thank you. So what do you do with measured foliations? In fact, I have a surface, and now I have a measured foliation on the surface. As I told you, it's a foliation. Also, with the fact that it is measured means that when I take a transverse curve, I get a number. I can measure the length. It's not the length. I can measure the measure of this transverse curve. Okay. So now I take this. I call it S. This set of simple closed curves. And we said, we agreed at the beginning that when I say simple closed curves, it means that they are not homotopic to a point. I'm not interested in closed curves which I can shrink to a point. And then I have a measured foliation. F. F is my measured foliation. And if I take gamma, an element here, there's something called I f of gamma, which is the intersection number of gamma with f. And what does this mean? I means intersection, and what does this mean? It means that this is the minimum or the infimum, but it will be a minimum, the minimum of the transverse measure over all curves in the homotopy class gamma. If, okay, let's come back to hyperbolic geometry. If the surface is equipped with a hyperbolic structure, and I take a simple closed curve gamma, then there's, I can get a number which is its length, the length of gamma with respect to this hyperbolic structure. Okay? Now, instead of a hyperbolic structure, I have a measured foliation. Gamma, say, is gamma is this curve like this. This is I can measure this. I can measure this transverse measure of gamma because it's I have this foliation. You see, I have this foliation, and I take the smallest one, in fact. Because gamma is a homotopy class, it's represented by curves which are not homotopic to a point. I take the infimum. Now you may tell me, okay, why is the infimum non-zero? In fact, it's like for simple closed curves on a hyperbolic surface. Why is the infimum of a homotopy class non-zero? Infimum of the length of a homotopy class non-zero? Because it's like this, because life is such that of course there's there's a proof which is not difficult at all, but the thing which I'm saying is that on S, on this space S, I have length functions. This we did in detail. And length functions associated with hyperbolic structures. And we have transverse measures associated with measured foliations.
So what if
Yes.
simple closed curve is part of the leaf of that foliage?
No. Yeah, you are right. It can be part of the leaf. It can be part of the leaf of the measured foliation. Then its transverse measure is 0. You are completely right. What I'm saying here is that. Okay, let me write it. Let me write it here. It's something which is analogous to what I said for hyperbolic structures. You remember I said that length spectrum determines the hyperbolic structure. Right? Now what I want to say is that transverse measure determines the measured foliation. That is, the spectrum of transverse measures on all these elements of S determines the measured foliations. And then you have the same questions as for hyperbolic structures. Given a measured foliations, to determine completely the measured foliation, how many transverse measures of curves do I need? The same question as we asked for the hyperbolic structures. And I mentioned, after a question, I mentioned the growth rate of the length spectrum of hyperbolic structures. There's an analogous theory for growth rate of transverse measures on the set of simple closed curves. Yes. Okay, so let me state this theorem about the compactification of Teichmüller space. So something which I will not talk too much about, but you see, as we said last time, I have a pair of pants, and then I can draw measured foliations on this pair of pants. You remember for hyperbolic structures, we said that the three lengths of the three boundary components of the pair of pants determines the pair of pants completely as a hyperbolic surface. Here also the length, well, the transverse measure of the three boundary components of the pair of pants determines the measured foliation. On the pair of pants. So you can glue measured foliations on pair of pants, and you have also Fenchel-Nielsen coordinates. Of course, Fenchel and Nielsen did not know anything about measured foliations, but you also have Fenchel-Nielsen coordinates for measured foliations. So I want to recall, I want to tell you, I'm skipping a little bit of the theory, but I want to tell you that theorem of Thurston on the compactification of Teichmüller space. Okay, so we have again S, simple closed curve on the surface. And I recall that simple closed curve means non-homotopic to a point. I have this space of, well, this is the space of positive functions, space of functions from S to the positive numbers. I'm using Thurston's notation. So I say that, well, Teichmüller space is a subset of this space. Do you understand this? I mean, I tried to explain this today, that any hyperbolic structure, any element of Teichmüller space gives me a function on the homotopy class of simple closed curve. This is the length function. Yes. And I explained to you also, I tried to explain that the length function determines the point on Teichmüller space, right? So I have here, I put equality is not equality. This is, I have an inclusion, in fact. This map is injective. Okay. It's an injective map. Now I have my space of measured foliation, which I call MF. And I also explained to you that intersection functions, in fact, I didn't say it this way, but the intersection function of a measured foliation on all homotopy classes on simple closed curves completely determines the measured foliation. I gave you just some idea on one pair of pants, and then you have to glue pair of pants and so on. There's some work to do here, like for the hyperbolic geometry case. Okay. What I'm saying by this inclusion is that if I have a measured foliation on the surface, and if I know its value on all the simple closed curves, then I know the value of this measured foliation. Do you believe this? It's something close to what I said for hyperbolic length, because of this, if I know the value of the measured foliation on these on the three components of the pair of pants, then there's a unique way to fit the measured foliation in the pair of pants. And then
same as the fundamental.
Where?
In R plus, the image.
Yeah, positive numbers. Yes, the positive numbers. Now, what I say here is that the images are disjoint. This was your question. The images are disjoint, in fact, and this is a theorem. This is part of the theory.
No, what I meant was that when you're taking length,
yes,
you're going to get countable set.
This set is countable, and this is the space of all functions on this. Yes.
The image in R plus for each means if you take for all S.
S is countable, yes. For any element of S, I'm taking. I have one value, yes. Okay, so now there's a little bit more there's a little bit more, and we are almost done. So instead of embedding in this space of functions on S, we embed in the projective space. That is, I want to consider that the projective space is the space of points up to a scalar constant. So what happens to hyperbolic structures? We said that if I give you the collection of all lengths of simple closed curves, then I know the hyperbolic structure. You remember this. If I give you all lengths of simple closed curves up to some multiplicative constant, do I determine the simple closed? Do I determine the hyperbolic structure? Yes, the answer is yes, because you see, for instance, you can think about the area of a hyperbolic surface. The area is fixed. So there's no way of doing dilations on a hyperbolic surface. If the lengths are, the length spectrum up to a constant will give you the length spectrum, right? There's only one hyperbolic structure up to homotopy, which gives you which is the length spectrum of some hyperbolic structure. Okay. So in fact, this is an injective map. This is an injective map.
So when you say that S is countable, are you actually taking the homotopy classes of this non-contracted?
Yes, yes, this is what I said. Yes, homotopy classes. Yes, I'm sorry. Yeah, this is homotopy classes. Homotopy classes. In each homotopy class, there's one simple closed curve. Yes, so I can. Yes, yeah. Yes, there's only one geodesic. There's only one geodesic. Yes. Okay, now here, this map is not injective. This map is not injective, obviously, because, well, from everything I told you about measured foliations, I can multiply the transverse measure by some constant. I get another measured foliation, right? So this is not injective. But there's this projective space, the projective space of measured foliation, that is the measured foliations up to a multiplicative constant. And the theorem now, the compactification theorem of Thurston is that is the following. So the image of Teichmüller space in this space, we called it P R plus to the S is homeomorphic to an open ball of dimension 6G minus 6. The image of PMF in the same space is homeomorphic to a sphere of dimension one dimension less. Is this 6G minus 5 or 6G minus 7? 6G minus 7. Okay. And in the image, I mean in this image, PMF is a closure in the sense of general topology. It is a closure of the image of T. So this is the Thurston compactification of Teichmüller space. I skipped a few points, you know. So for instance, I didn't tell you that the measured foliations, of course, I have some flexibility. I mean, they are, when I say that the image of PMF, you see, PMF up to some homotopy, up to some isotopy of the measured foliations. Because when I say that a measured foliation is determined by the intersection numbers with homotopy classes of simple closed curves, if I take a homotopic measured foliation, then it will give me the same numbers, the same intersection functions with homotopy classes of simple closed curves. So this is so in the same way as we had a marking here, and we said that we are identifying two hyperbolic structures if they are homotopic, right? Here as well, I'm identifying two measured foliations if they are homotopic. So okay, this is the I gave you three references for Thurston, and now there's this fourth one and the last one. This is called, or it's also a book on the internet. It's called Thurston's theory on surfaces. It's not written by him. These are notes written by Fatih, Lodenbach, and Poinaru. So it contains. So what I tried to say is explained there in maybe the first 100 pages. If you are interested, this is a very good thing to learn. You can ask me questions about this now or later or whatever.